Assalamualaikum and hello. As I promised, I will share with you on how to derive the hydrostatic force on plane surface. Okay. So hydrostatic force on submerged surfaces is divided into the surfaces are divided into two. One is plane, another one is curve. So before we proceed with both surfaces, we need to know how do we get the hydrostatic force equation. Okay, so hydrostatic force equation actually comes from um, F equals to PA. Pressure is force divided by area. So force is the normal force. Area is the cross-sectional area. So force is equal to pressure times area. So this force is called as hydrostatic. It's because hydro means water. And so normally it is applied to fluid lah, and the fluid is normally water lah. And static means the fluid is not moving or at rest. And normally for fluid that is contained in a tank, in a tank we have bottom and also side, the side of the tank. So at the bottom, so since the elevation or the height is of the same height lah, the elevation is at the same height, so therefore the pressure is distributed equally. Okay, so by the way, this can be a fluid lah, water. Okay, so since the water is distributed equally, okay, the force is concentrated at the centroid, at the center, which is somewhere here. Okay, so at the centroid. So this is the hydrostatic force acting on the bottom wall of the tank. However, for the side, since we have changes in the elevation, here elevation is 0, here elevation increases. Okay, so more than 0 lah. Alright, so because of that, and this water is open to the atmosphere, so the only pressure is the atmospheric pressure. Okay, so atmospheric pressure, if you assume gauge, and then it's 0. Okay, alright, so since pressure is 0 at the top, as you go down, pressure will be increased. Okay, as you go down, pressure will be increased. Here should be bigger, and bigger. Okay, so therefore this pressure is not if you want to calculate the force, since the pressure is not distributed equally, so the force is not concentrated at the centroid. Okay, so since it's not concentrated at the centroid, it is slightly lower, and because the pressure is higher at the bottom, because pressure increases with depth. So slightly lower, let's say this is the centroid. This force can be acting somewhere here. Can be acting somewhere here. So if I draw the force, the hydrostatic force perpendicular to the wall, and it is through the CP. We call it CP. Okay, this is the centroid. This is the CP. Okay. CP means center of pressure. Okay, CP, center of pressure. Okay. So if you can see here, this is this one, the wall is vertical. This one, the wall is horizontal. Okay. So what happen if you have something like this? It is slightly tilted. It is tilted at a certain angle. Okay, from the horizontal. So it's not vertical, it's not horizontal. It is at a certain angle from the horizontal. Okay. So let's say this is the wall or the gate or the plane surface of any arbitrary shape. Can be of any shape. Okay. So how do you want to find the hydrostatic force? Okay. So this is hydrostatic force. By the way, this is hydrostatic force. Or you can also say resultant hydrostatic force. Because it's a resultant force of all the pressure distributed on the wall. Okay. So in this case, we want to find the force, okay, the hydrostatic force Fr. However, okay, similar to this, okay, since the pressure is not equally distributed, okay, we cannot just use direct calculation. Okay, we have to use df differential equation, and p has to be distributed. P has to be average p lah. Okay, this bar means average. Alright. Okay, so F, this F is the resultant force or the hydrostatic force. Okay. If you still remember, in the previous lecture, we learned about pressure variation with elevation, where P is equal to rho g h. Okay. So P is equal to rho g h. So in this case, I want to replace this P with rho g h, and since it's in the yeah, I replace it first. Rho GH dA. So if you can see here, this H is actually the height from the water surface to to any points on the surface of the plane lah. So in this case, this is the H. And if you can see here, the slanted height here, which is the height or the distance uh, that is taken from the intersection of the water and the line of action of the the line of the gate or the plane here. Okay, this is the gate or the plane. You extend it and then it meets the water surface. Okay, so this should be your point O. So from here, you draw a perpendicular line. Okay, so from this perpendicular line, you draw another parallel line through the point at which you take the height just now. Okay, so that should be your Y. Okay, if you draw a triangle, this should be Y. Okay, this should be H, right? Okay, so the angle of the angle should be here. Okay, so H you divide by Y is you get sine theta. Okay, so basically H is Y sine theta. So I replace this H with Y sine theta. So I got rho G. I put the sine theta first and then put the Y inside here. Okay, so this term I circle it. This term is called as first moment of area. Okay, first moment of the area. Okay. first moment of the area is equal to y bar a. Or in certain textbook it uses YC. C means centroid, bar means average. We take at the average, which is at the centroid. Okay, so therefore the equation now becomes rho g y bar sine theta times with a. Okay, so if you refer to this triangle, you try to do another triangle by using h bar and y bar. Okay, you use the same triangle with the same theta. So h bar divided by y bar is also the same as sine theta. Therefore, y bar is equals to y bar sine theta. So y bar sine theta is equal to h bar. Okay. So what does it mean by y bar and h bar? So just now, we use h. Now we use h bar or y bar, or also can be called as hc and yc. Okay. So is the h bar is the vertical height that is taken from the water surface to the centroid of the gate lah, or the plane. So in this case, this is the point. Okay, the centroid of the gate, or the body lah, or the wall. Okay. While the y bar or yc is the slanted height, or we can call it as the distance from the point O here to the centroid, to the centroid of the wall. Alright. So you can also replace this equation with Fr equals to rho g. So this y bar sine theta I replace with h bar. So I got h bar a. Alright. So this is how I get the hydrostatic force equation. This equation is called as hydrostatic force. Okay. Instead of using rho g, you can also use gamma. Gamma h bar a. And the unit is in Newton. Okay, so this is the magnitude of the hydrostatic force. Even though we use the height that is taken from the water surface to the centroid of the wall or the plane surface. However, the force is not acting at this point. Okay, it must be slightly lower than the centroid at the CP, through the CP. As I have explained here, as you go deeper, the pressure will increase. Therefore, the force must be concentrated slightly lower than the centroid. So you can see here, the location of the hydrostatic force is slightly lower than the centroid. So you need to know how to measure the difference. So this difference is called as YCP. Okay, the difference from the centroid to the line of action of the hydrostatic force. So how do you, why do you need to find the location? Because sometimes in the question it will ask you the location of the line of action of the force, the location of the force. Sometimes you also need to find moment. Moment is force times distance, so you need to know this distance. So how do you get this? Okay. Like I mentioned just now, we use moment. Okay, moment. So we take the moment about the point O. Okay, so if I want to find Fr, okay, we use moment. Fr we times with the distance. If you take moment about point O, okay, so force times this distance, which is taken from point O to the force. Okay, so that is yr, this one yr. So force times yr, you get moment. You get moment. It's equal to, if I go back to this equation, okay, it's equal to y times df, which is the general f here at any point. Okay, the df you times with y. Okay, similar to this is df. Df you times with y. Okay, since it's in differential form, you have to integrate with respect to the area. Okay, so this will become df just now is rho gh dA, right? Okay, df just now is rho gh dA. Okay, while rho gh dA. Okay, and then we have y. df is just now is rho gh dA, and then we have y. Okay, however, we want to ensure that we use the same notation, which is a parameter or property, which is y. So h will be will be replaced with y sine theta. So now we get rho g y, another y here, and then sine theta dA. Okay, so I put the constant outside, rho g sine theta. So I have this y square dA. Okay, so this equation or this term, yes, now it's the first moment of area, right? So now it's the second moment of area. Okay, so second moment of area can also be called as moment of inertia. Ix with respect to the axis lah, this axis. Let's say this is x-axis. Okay. Alright. So therefore, if I where can I draw again? Let me erase this. Okay, you guys know this is the triangle, the triangle. Okay, alright. So this one I continue here, so I should get so y r, okay, so yr is equal to rho g, okay, sine theta, and then I have ix. Okay, while the f here, okay, I replace with rho g a y bar sine theta. So how do I get this? Okay, it actually comes from here. Fr is rho g y bar sine theta a. Okay, so I put this, not this one, because I want to eliminate the sign. Okay, eliminate this, cancel this. So what do I get here is ix divided by y bar a. Okay, so ix divided by y bar a. So by the way, this ix can also be written as ixc plus A times y bar square. Okay. IXC is the second moment of area with respect to the axis passing through its centroid and parallel to the x-axis. Okay, meaning that IXC back to an axis passing through its centroid. IXC passing through the centroid. Basically, IXC is taken because we are taking the what we call that, um, the axis that pass through the centroid and parallel to the x-axis. Okay, all right. So we replace this into the equation. So we should get IXC plus A y bar square divided by y bar A. Okay. So IXC divided by y bar A, okay, plus y bar. Okay. So basically this has been cancelled lah. A and y bar, another y bar here. So what is left is y bar. Okay. So this is for YR. Okay, if you can see here YR, okay, if you can see here YR is basically YC, okay, this YC plus YCP, okay, or YR lah, Y bar, Y bar plus YCP. So therefore, it looks similar here. Okay, this is YCP, IXC divided by Y bar A, and this is Y bar. So you can write it as YCP plus Y bar. Okay, so this is how you get the YCP equation, where uh, YCP is equal to IXC divided by Y bar A. Okay, this one. So this is the location of the hydrostatic force from the centroid to the line of action of the force, which is the CP. Okay, these two are the derivation will not be asked, will not be assessed, but you need to know how to use the equation. Okay, so this can be of any arbitrary shape. Like in example, normally we use rectangle, circle, or triangle, common shapes, because you can actually use um, the figures that consist of the area formula and also the IXC formula that will be provided in the exam. Alright, so that's it for the derivation. Hopefully you get something lah from this, and I see you guys in class.